I think it'll be able to produce a car ultimately in less than 5 seconds. Like, can you imagine a car coming off the line in less than 5 seconds? That's like, whoa.
When Elon Musk first teased that Tesla was tinkering with a die-casting beast as heavy as 10 Boeing 747s, stretching 40 meters nose to tail, and squeezing its mold with the weight of the Eiffel Tower, even veteran auto engineers scoffed. Yet, picture a Tesla Model 2 priced just over 10 grand, profit margins that have tripled, and an assembly line so blisteringly quick that people can't even stand beside it, while scrap rates slide below 2%. And most importantly, this monster machine has already been humming away inside a Tesla plant for more than a year. Installation is entering its final phase, and the technical white papers, production plans, on-site photos, and recorded interviews Tesla's about to release will show America and the world exactly how the company is smartphonizing the car business. So how did Tesla pull this off? What benefits do we get from the new versions of Tesla's Giga Press machine? First, the 50,000-ton Giga Press encapsulates a radical step change in die-casting scale, yet its core mechanism remains elegantly simple. In principle, the workflow of Tesla's latest press is identical to the 6,000 and 9,000-ton models already producing Model Y rear underbodies and Cybertruck exoskeleton pieces. Aluminum ingots are melted in a gas-fired furnace at roughly 850 degrees Celsius, held in an electrically heated chamber at 750 to 850 degrees Celsius, filtered through nitrogen and argon to remove oxides and particles, injected at high speed into a lubricated steel mold, solidified, cooled, trimmed, X-rayed, and recycled. What distinguishes the new machine is scale. Engineers estimate a footprint of 40 meters by 13, a 12-meter height, and a mass approaching 3,700 tons, comparable to a small office block laid on its side. At full stroke, the hydraulic system clamps the die halves together with a force 8.3 times greater than the original Fremont 6,000-ton press, ensuring that the mold doesn't even think about breathing, as an internal engineer quipped during a factory walkthrough. Musk's own description conveys how violent the process looks in real time.
So, I mean, we got to jam the liquid metal in, cool it down real fast, like real fast.
That seemingly casual remark belies months of thermal flow modeling, contour-based cooling channel design, and sensor-laden mold cavities that feed data to a proprietary AI inspection suite, which checks porosity, flow fronts, and shrink lines in seconds. In short, the 50,000-ton press magnifies every variable: temperature gradients, piston velocity, degassing chemistry, demanding an orchestration so precise that human operators can observe only from distant control rooms, while robots service the machine between 90-second cycles. Second, such scale enables a manufacturing tempo that reframes the economics of mass-market electric vehicles, particularly Tesla's forthcoming Model 2 and Cybercab. The current 6,000-ton presses at Gigafactory Shanghai eject a Model Y rear underbody every 35 seconds. A pair of mirrored lines yields roughly 870,000 units per year.
In a single casting machine, we could do like 5 at a time or something. I'm trying to think, like, how do you scale castings? Because you got liquid metal, metal's got to cool, and then you've got to automate, getting all the bits and pieces off the casting so it's usable.
Yet Musk insists that the claim initially sounded theatrical, but underlying math supports it. By combining the entire front and rear third of the chassis into 2 single-piece castings, then designing a floor pan that doubles as the battery enclosure, Tesla reduces the number of major structural parts in the Model 2 from more than 200 to around 80, according to a senior manufacturing engineer on the next-gen team. Fewer parts mean fewer welds, fewer robots, shorter times, and less factory floor space. Exactly why Musk boasted in the third quarter 2024 earnings call that the line needs 300 robots instead of 1,000. In the same conversation, he lamented that conventional auto lines look like a 19th century watch factory, whereas the cybercab line doesn't look like a normal car manufacturing line. It looks like a really high-speed consumer electronics line, so fast that people can't even get close to it.
The design of the cybercab line, it doesn't look like a normal car manufacturing line. It looks like a really high-speed consumer electronics line. In fact, the line will move so fast that that actually people can't even get close to it.
Because each chassis emerges with most mounting bosses, wire harness guides, and crash crumple zones already cast in, downstream operations collapse into an unboxed stage. Paint, battery drop, interior module insertion, wheel fitment, end-of-line test, done. Internal planning documents leaked last February suggest a target of 178,000 Model 2 vehicles per week, once 2 presses feed 2 mirror image assembly corridors, implying 7 million units per year on 40 weeks of operation, a figure that dwarfs the combined global output of Model 3 and Model Y today. Third, the advent of this machine is pressuring every major automaker to reassess tooling strategy. Yet the gap between adopting a large press and replicating Tesla's vertically integrated ecosystem remains vast. Within months of Tesla's Fremont demonstration in late 2020, companies from General Motors and Hyundai to Volvo, Zeekr, and XPeng placed orders for 6,000 to 9,000 ton presses. XPeng even surprised analysts by commissioning a 16,000 ton unit. Yet none has announced a 50,000 ton deployment, partly because the hardware alone is insufficient. Idra, Buhler, and LK Machinery can sell a press, but only Tesla has spent a decade building the software infrastructure that schedules smelting, predicts die wear, routes castings to AI X-ray booths, and recycles sprues back into the melting furnace with minimal energy loss. Early critics argued that aluminum dies would erode faster than steel stamping dies, erasing cost savings. Tesla answered by lining critical surfaces with a hybrid nickel-cobalt alloy, monitored by eddy current sensors, and by demonstrating net cost reductions of 40% on Model Y rear underbodies. Those numbers convinced Ford, Toyota, Volkswagen, and Stellantis to buy smaller gigapresses, yet executives admit privately that integrating them into century-old plant layouts is like transplant surgery. Meanwhile, Chinese upstarts unburdened by legacy lines can iterate quickly.
And that's actually kind of how they do it in like small volume castings. They'll have a casting block that'll make 100 Matchbox cars at a time. And we just make that real big. Yeah, we have the cathedral of casting back there.
The remark notes an inversion of the usual automotive hierarchy. Instead of stamping presses arranged around a central line, the gigapress becomes the cathedral, and every other station bows to its rhythm. Such architecture echoes printed circuit board fabs more than Detroit body shops, indicating that vehicle plants may evolve into semiconductor-style gigafabs, where capital efficiency hinges on machine cycle time, not labor cost. Environmentally, high-tonnage casting dovetails with Tesla's broader sustainability rubric. A casting-rich chassis reduces mass, which cuts battery size for a given range, which lowers upstream mining demand. Geopolitically, the ability to produce millions of sub-$30,000 EVs per year could accelerate EV uptake across India, Southeast Asia, and South America, regions currently priced out of premium electrics. Yet it also forces policymakers to confront a future in which production is hyper-concentrated in plants, run by fleets of robots and supervised by a handful of engineers. Factories that can be switched on like cloud servers, and, in Musk's words, move so fast that no one can get close. It positions Tesla to manufacture the Model 2 and Cybercab at volumes once reserved for smartphones, compels rivals to tear up century-old body shop blueprints, and sketches a roadmap towards scalable circular global electrification. Skeptics still caution the die life. Thermal shock and metal turbulence pose formidable risks. Yet the same was said when Tesla installed its first 6,000-ton press in 2020, and today that machine hums around the clock in Fremont, stamping out castings that underpin the world's best-selling passenger vehicle. How will Tesla's 50,000-ton gigapress make our next EV cheaper and better? Nobody at Tesla's Giga Texas plant forgets the day the first 50,000-ton gigapress module rolled in on a convoy of 8 flatbed trucks, each painted bright orange to warn motorists that they were trailing a single component heavier than 2 locomotives. Until that week, the shop floor's reigning heavy weight had been the 9,000-ton Cybertruck press, itself a monster at 688 metric tons. The older 6,000-ton units that stamp out Model Y rear underbodies weigh only 430 tons and measure 19.5 meters long. The new frame, however, came in at nearly 3,700 tons and stood higher than a 4-story townhouse once it was upright. Crews poured a 12-foot-thick steel-reinforced concrete slab weeks in advance, tying in post-tension cables that disappear under the shop's polished epoxy floor. Without that foundation, the hydraulic recoil of 50,000 tons of clamp force would have cracked the building like a china teacup. Installation took the better part of 11 months. First came the twin furnaces, a gas-fired melter that liquefies virgin and remelt aluminium at 850 degrees Celsius, and an electrically heated holding furnace that keeps the alloy between 750 degrees Celsius and 820 degrees Celsius beneath a nitrogen blanket. A rotary degasser injects argon through a spinning impeller, while a silicon carbide filter catches particles larger than 25 microns. From there, molten metal snakes through heat-traced pipes into the shot chamber, where a piston, lubricated with precisely 8 milliliters of synthetic oil, rams a 500-kilogram slug of alloy into a mirror-polished steel die. Before every shot, a robot fogs the cavity with 35 milliliters of soybean oil, the same food-grade compound you would find in a fast food fryer, because crude vegetable oil carbonizes evenly and peels off in a single swipe when the casting pops free. What happens next is a marvel of controlled violence. The die halves slam together with a force 8.3 times higher than the original Fremont press, sealing the joint so tightly that technicians call it hermetic steel. Inside, liquid aluminium jets, downrunners at over 10 meters per second, fills bosses, gussets, and crash-absorbing foam pockets, then freezes solid against wafer-thin cooling channels milled into the die. Those channels now follow the part's contours, a Tesla invention that cut the 6,000-ton cycle time from 170 seconds to 75, and they are fed by a glycol loop chilled to near freezing with reclaimed rooftop rainwater. 32 seconds after the shot, the die cracks open. Ejector pins push a glowing orange frame onto a roller bed, and the entire casting plunges into a quench tank. Water hisses to steam as the metal surface drops from 400 degrees Celsius to 50 degrees Celsius in under 90 seconds, arresting microporosity before it can grow. Exhaust runners and biscuit are sheared off by a 6-axis robot, ground into chips and shuttled back to the melter. 20% of every new chassis is literally yesterday's trimmed scrap. Because the 50,000-ton press fires 5 dies in parallel, front frame left and right, rear frame left and right, plus a central battery through. One complete Model 2 skeleton leaves the casting cell every 5 seconds. That works out to roughly 12 finished cars per minute, or 720 an hour. For comparison, the older Model Y line in Shanghai launches a rear underbody every 35 seconds and tops out at 870,000 cars per year. The new arrangement with 2 presses feeding twin mirrored corridors was spec'd for 7 million Model 2 and Cybercab units across 40 production weeks. The leapfrog in time let Tesla scrap 600 welding robots that once stitched together 21 separate stampings. It also nudged profit margins on entry EVs from the low 20s to an internal target north of 30%, even after the headline sticker falls below $15,000. The engineering dividend spills beyond balance sheet arithmetic. In March, Lars Moravy's team unveiled a redesigned Model Y rear frame that is 7 kilograms lighter and 20% stiffer in torsion. Thanks to rib geometry, the die can now form in one go. Similar topology optimization on the Model 3 front cradle knocked out enough mass to extend real-world range by 4%, more than the gain Tesla once earned by switching an entire wheel set to forged aluminum. Quality control kept pace. Each casting is X-rayed by a pair of 9 MeV linear accelerators, whose images are parsed by a neural network trained on 500,000 labeled rejects from 2022. In the casting cathedral's control mezzanine, operators joke that they are now farmers of aluminum, harvesting bright orange frames that glide past like loaves of bread. Every 2 hours, a pit crew swaps dies, vacuum polishes the cavities, and logs tool wear depth in a cloud dashboard that predicts failure 3 shifts ahead. On the rare occasion a shot misfires, the piston velocity curve pops red on a wall-sized display, and a shutdown sequence triggers before molten metal can harden in the runners. The press's heartbeat, an infrasonic thump you can feel in your chest, pauses for 7 minutes while maintenance robots dislodge the plug and brush the runners clean. Then the cathedral roars back to life, spitting out another car every 5 seconds, hurtling Tesla toward a production scale the auto industry once thought impossible. When analysts ask Elon Musk why he risked billions on a technique most rivals wrote off as impractical, he likes to point to the Hot Wheels die-cast Model S on his desk. "Kids have been casting entire cars since the 60s, he laughs. "We just made the toy a little bigger." Standing beneath the cantilevered gantry of the 50,000-ton press with aluminum lightning flashing behind a plexiglass curtain, the joke feels both wildly modest and entirely true. If Tesla really can stamp out a complete Model 2 every 5 seconds, would you trust a car built that fast? Or does the speed raise quality concerns for you? Please share your opinion in the comment section below this video. This coming October, Tesla will launch the Model 2, an affordable car priced at just around $25,000. But behind that attractive price tag lies an incredible technological story. Tesla will manufacture the Model 2 using a massive gigapress machine, capable of exerting up to 50,000 tons of pressure. According to Elon Musk, these cars will be sold at an affordable price point, which means demand will be enormous. Tesla needs a machine that can produce fast enough before facing millions of orders. This isn't just any ordinary machine. It can create an entire car in just a matter of seconds. Yes, you heard that right. Let's dive into how Tesla is building a $25,000 car right now. Welcome to the world of Tesla cars. For many from the generation that witnessed the golden age of classic Chevrolets, busy assembly plants, and the sound of welding machines ringing out day and night, the idea of casting an entire underbody in just a few seconds may sound like pure science fiction. But Elon Musk and Tesla are making it a reality.
Like real fast. And then I guess maybe we need to just get even bigger casting machines. Sure, why not? Let's 50,000 tons. I think it'll be able to produce a car ultimately in less than 5 seconds. Can you imagine a car coming off the line in less than 5 seconds? That's like, whoa.
What's remarkable is that it all started with something incredibly ordinary. One day, Elon Musk was looking at a Hot Wheels Model S toy car, made using die casting or injection molding, which is why they're cheap and widely available. At that moment, Musk had a thought. Why doesn't Tesla do the same with the Model Y? What seemed like a casual question ended up planting the seed for an industrial revolution. Shortly after, Elon Musk began searching for a partner that could build a machine big enough to bring this idea to life. 5 companies flat out said no. Only one, Idra Group, a company in Italy, dared to respond with a simple maybe. And with that maybe, the journey to change the future of car manufacturing began. It all started with the 6,000-ton gigapress, which Tesla used to cast the rear underbody of the Model Y. This machine replaced more than 70 individual parts with a single solid piece of aluminum, dramatically simplifying the assembly line. Next came the 9,000-ton gigapress, specially designed to cast the body of the Cybertruck, a vehicle massive in size and made from stainless steel. The 9,000-ton press was already hugged, but what about the upcoming 50,000-ton Giga press? Just how powerful will it be? And how can it possibly cast 5 Model 2's underbody at the same time? Tesla's affordable new car, unofficially known as the Model 2, features a compact design with short front and rear overhangs. Compared to the Model Y, which has over 200 structural components, the Model 2 uses only about 80, a reduction of more than 60%. This dramatically simplifies assembly and significantly cuts production costs. Tesla used the 6,000-ton gigapress to produce the rear underbody of the Model Y and the 9,000-ton press to cast parts of the Cybertruck's structure. Both machines have proven highly effective cutting costs, speeding up production time, and delivering high-performance vehicle frames for the Model Y and Cybertruck. So you might be wondering, if the Model 2 is smaller than the Model Y, why doesn't Tesla just use the 6,000-ton gigapress to build it? Why go all the way up to a machine with 8 times the clamping force? It's a fair question, but here's the explanation. At its core, the gigapress is a high-pressure die casting machine. Die casting has long been an essential part of the auto industry's history, used to create critical parts like engine blocks, transmission housings, and front or rear vehicle subframes. However, up until now, Tesla's 6,000-ton and 9,000-ton gigapresses have only been able to cast sections of a vehicle's frame, not the entire thing. But Tesla has bigger ambitions for the Model 2. It wants to cast the entire underbody of the car in a single shot. Naturally, the existing machines aren't powerful enough to pull that off. That's why Tesla needed a much larger machine with greater clamping force and multiple molds operating on a single press. And that's exactly why Elon Musk ordered the 50,000-ton gigapress. While other automakers, especially in China, have tried to imitate Tesla's approach, no one has been able to keep up. Why? Because Elon Musk keeps pushing the limits, continuously upgrading the machine itself. The gigapress manufacturing process isn't just an innovation in the EV industry. It's a major leap forward in both technology and production efficiency. At the heart of this technology is the process of melting an aluminum alloy at extremely high temperatures inside an industrial furnace. Once the aluminum reaches a molten state, it's poured into a precisely engineered metal mold shaped to match the part being produced, such as a vehicle frame. The gigapress then applies immense pressure, ensuring that the molten aluminum fills every tiny detail of the mold, leaving no defects behind. What's critical here is achieving perfect balance. If the casting is done too quickly, air bubbles can form. If too slowly, the aluminum begins to cool before filling the entire mold. That's why the gigapress relies on a highly controlled cooling system to ensure that the solidification process happens evenly and consistently. This precision not only guarantees high quality, but also results in durable, structurally sound components. Once cooled, a robotic arm automatically removes the part from the mold, trims off any excess material, and transfers it to a quality control station to ensure every detail meets exact standards. One of the key advantages of the gigapress is its ability to reduce vehicle weight, increase structural rigidity, and improve overall performance. By casting a single large part instead of welding together dozens of smaller components, Tesla saves time, minimizes errors, and boosts production efficiency, pushing EV manufacturing into a new era. Today, giga-casting technology is no longer exclusive to Tesla. Major automakers like General Motors, Hyundai, Volvo, Zeekr, and XPeng have all made significant investments in their own giga-casting systems. Among them, XPeng has made headlines by installing a 16,000-ton giga press, an advanced piece of technology that's hard to ignore. However, Tesla remains the pioneer, pushing the boundaries of this technology even further with the upcoming 50,000-ton giga press. A bold move that no one saw coming. When Elon Musk first mentioned the 50,000-ton gigapress, we all had the same questions. How massive will this machine be? Where will Tesla install it? How long will setup take? And how on earth can it produce tens of thousands of Model 2 units each week? With the launch of the 50,000-ton gigapress, Musk made it clear. This new production line will operate at a speed so fast that humans won't be able to get close to it. Everything will be fully automated and, quite frankly, dizzying to witness. Every step of the process, from pouring the molten metal, cooling the mold, to extracting the finished part, will be fully automated. And here's the most jaw-dropping part. Each production cycle will take only about 5 seconds. That means a full vehicle underbody could be completed in the time it takes you to blink a few times. With the 50,000-ton gigapress, it's easy to imagine a colossal machine roughly the size of a 3- or 4-story building laid on its side. Tesla will need to build a dedicated facility just to house it, likely requiring a heavily reinforced concrete foundation dug several meters deep to support the machine's immense weight. To put it in perspective, the 50,000-ton gigapress exerts about 8.3 times more pressure than Tesla's 6,000-ton machine and 5.5 times more than the 9,000-ton version. It's estimated that this machine could be around 65 feet long, 39 to 49 feet high, and 33 to 39 feet wide, with a total weight exceeding 3,000 tons. While the operating principles of the 50,000-ton gigapress remain similar to those of the 6,000 and 9,000-ton models, it features major advancements in scale and output. For example, whereas traditional die-casting machines typically operate with a single mold, the 50,000-ton version will have at least 5 molds, allowing it to cast 5 vehicle underbodies in a single cycle. The process begins with material preparation. Tesla melts down fresh aluminum ingots along with recycled aluminum from previous casting cycles in a furnace, reaching temperatures around 1,562 degrees Fahrenheit. Once molten, surface impurities are removed, and the purified liquid metal is transferred through heated pipelines into a sealed holding furnace, where temperatures are maintained between 1,382 degrees Fahrenheit and 1,562 degrees Fahrenheit. The gigapress uses a 2-furnace system to handle the aluminum alloy. One furnace melts the aluminum, powered by natural gas, while the second furnace, heated electrically, keeps the molten metal at a consistent temperature for casting, as mentioned above. The interior of the holding furnace is filled with nitrogen gas, which helps prevent oxidation in the molten aluminum and maintains a stable temperature. Additionally, argon gas, a rotary degassing machine, and a silicon carbide filter are used to remove impurities and particles larger than 25 microns, ensuring the metal's high quality. Once the material preparation is complete, the next step is mold preparation. Before each casting cycle, the gigapress applies a thin, even layer of lubricant to the mold surface using a robot that sprays about 35 milliliters of soybean oil, much like greasing a baking pan, to make it easier to remove the finished part afterward. Next, a vacuum system activates to remove air from the mold cavity, and then the molten aluminum is transferred from the holding furnace into the gigapress's injection chamber. Here, the liquid metal is injected into the mold cavity by a high-speed piston. The piston itself is lubricated with about 8 milliliters of oil before each injection to ensure smooth and efficient operation during the casting process. The casting process used by Tesla's 50,000-ton gigapress is not only advanced but also far more complex than standard die-casting machines. Due to its enormous size and power, this press demands extremely tight control at every stage. One of the biggest challenges is that the molten aluminum must travel a longer distance than in smaller machines, increasing the risk of defects during casting. If the molten aluminum is injected into the mold too quickly, there's a high risk of air bubbles forming, which would weaken the final part's strength and durability. Conversely, if the injection process is too slow, the aluminum may begin to cool before completely filling the mold, resulting in incomplete or uneven parts. That's why the 50,000-ton gigapress casting system must operate with extremely high precision. Every movement, every second, needs to be carefully controlled. After the aluminum is injected, it remains in the mold until it fully solidifies. The rough casting is ejected from the mold when it reaches about 752 degrees Fahrenheit and is immediately transferred to a cooling bath to rapidly reduce its temperature from 752 degrees Fahrenheit down to around 122 degrees Fahrenheit. This rapid cooling process not only effectively cools the material, but also helps eliminate certain defects that might form during solidification, while improving the aluminum's mechanical properties such as strength and hardness. Once the casting has finished cooling, the mold opens and is cooled down to around 365 degrees Fahrenheit. A robot then thoroughly cleans the mold, removing any impurities or leftover material, preparing it for the next casting cycle. This ensures that each subsequent cycle runs smoothly without any interference from leftover debris or contaminants from the previous cycle. Typically, a new casting cycle begins just 1 to 2 minutes after the previous one finishes, keeping the production line operating at maximum speed and efficiency. Any excess metal left after casting is cut off and recycled to be melted down again in the next batch, ensuring maximum efficiency and material savings. After the casting process is complete, the final product undergoes quality inspection using X-ray imaging, which accurately detects strength and any potential structural defects, ensuring the part meets the strictest standards. One of the biggest challenges during casting is preventing the mold from separating under the extreme clamping force applied when injecting molten aluminum. That's why the die casting machine must exert very strong clamping force to keep the mold tightly sealed and stable throughout the entire process. With the 50,000-ton Giga press, this clamping force is exceptionally high, far beyond that of conventional casting machines, to ensure the mold stays perfectly aligned and can withstand the enormous pressure without deforming or breaking. This not only guarantees precise casting, but also ensures the quality and durability of every part produced.
So I mean, we got to jam the liquid metal in, cool it down real fast, like real fast.
According to Elon Musk, to achieve outstanding casting speed and efficiency, Tesla had to design a super-fast cooling system, an intelligent mold release mechanism, and an AI-powered automated quality inspection process, a technological combination that no other automaker has attempted at this scale. This innovation is not only a technological breakthrough, but also a turning point in automotive manufacturing. Using AI to automate quality checks and employing smart mold release mechanisms optimizes production, minimizes errors, and ensures the highest product quality. This also marks the first time in the automotive industry that Tesla has shifted to a production model similar to electronics manufacturing, fast, lean, and space-efficient. This model not only reduces production time and costs, but also opens the door to mass-producing high-quality automotive parts at unprecedented speeds, creating a new future for the global automotive industry. Besides owning the new 50,000-ton Giga press, Tesla's VP, Lars Moravy revealed that the rear Giga casting of the new Model Y has been significantly redesigned. The rear frame is now about 15 pounds lighter than the previous version, while machining time has been reduced by over 50%. This weight reduction of up to 15% not only improves the vehicle's performance and range, but also enhances the structural rigidity of the rear, reducing body twist during sharp cornering and delivering superior handling. In an interview, Lars Moravy shared that Tesla's Giga casting process has seen major improvements since 2020. Specifically, Tesla now uses advanced cooling technology, where cooling channels follow the shape of the mold, cutting the cycle time from 170 seconds down to just 75 seconds on the 6,000-ton machine. As a result, the Model Y is not only lighter but also more precise and consistent, boosting production efficiency and product quality. Surprisingly, Tesla has not applied Giga casting to the front section of the new Model Y, a rather unusual move given that Tesla pioneered this technology. However, Lars Moravy explained that most current Model Y production lines still use stamped sheet metal for the front, rather than Giga casting, due to technical and economic factors that have so far limited the expansion of this technology to other parts of the vehicle. Tesla has unveiled its 6-seat Model Y variant in China, known as the Model YL. This new variant of one of the world's best-selling vehicles comes with a longer wheelbase, adjusted C-pillar design, and most importantly, a 6-seat interior layout. The addition of a longer wheelbase and a more spacious third row is a fantastic addition for the Model Y's family utility and positions this variant as sort of a mini Model X. But let's compare the sizes to really know how this new Model Y compares to a Model X. The defining feature of the new Model YL is its 6-seat configuration. This layout has previously been exclusive to the larger and more expensive Model X. While Tesla has offered the Model Y in a 7-seat configuration before, the third row was much too small to be utilized by anyone but small children. While this Model YL is slightly smaller than the Model X, it doesn't necessarily mean that it's smaller inside. The Model X features a much larger front end than the Model Y, accounting for several inches. When you line up the front wheelbase of the Model X with this new Model Y, the vehicles are almost exactly the same length. Tesla has designed this Model Y to be a bit more compact and efficient than the Model X, and likely much cheaper, while featuring the well-loved design of the new Model Y. Above all, from our perspective, the 50,000-ton Gigapress sets a new standard for speed, efficiency, and cost. With the ability to cast the entire chassis of the Model 2 in under 5 seconds, this machine not only redefines EV manufacturing, but also puts unprecedented pressure on Chinese automakers. By reducing over 60% of structural parts and eliminating hundreds of robots from the assembly line, Gigapress delivers superior simplicity and durability, enabling Tesla to produce affordable cars at an unprecedented scale. This creates a major challenge for competitors like BYD, NIO, and XPeng, who are striving to replicate high-pressure casting technology. The success or failure of Chinese manufacturers in producing low-cost EVs largely depends on their ability to catch up with this technology. Despite strong support from a huge domestic market and favorable policies, they still face technical barriers, such as replicating Tesla's proprietary aluminum alloys and many other technical factors known only to Tesla. Massive subsidies for electric vehicles, the very pride of America's EV industry, unrivaled anywhere else, are now being stripped away piece by the Orange Man, Donald Trump. In that context, what becomes of affordable EVs like the Tesla Model 2, promised at a $25,000 starting price, or even $15,000 or $17,000, once that subsidy shield is gone? Nothing will truly convince until we get clear answers to those questions. So, what is Tesla hiding about its plan to build 15 cars every 60 seconds?
I think it'll be able to produce a car ultimately in less than 5 seconds. Can you imagine a car coming off the line in less than 5 seconds? That's like, whoa.
In response to those doubts, Elon Musk promised to lower the price of electric vehicles to $25,000, or even as low as $17,000, by using a 50,000-ton Giga press to cast aluminum frames. This approach aims to capitalize on massive cost savings from eliminating screws, bolts, and washers. With scrap aluminum prices close to zero, using a single-piece cast frame stands as a clear commitment to long-term efficiency and cost-effectiveness in EV manufacturing.
And we also take our expertise in electric motors, in batteries, power electronics, structural design, and then another major important thing is that we're very good at manufacturing.
Essentially, this is Tesla's current secret weapon in gaining a competitive edge in electric vehicle manufacturing. This technology didn't even exist until 2020. And so far, Tesla has been the exclusive user of it in their effort to streamline production of their best-selling model, the Model 3, Model Y, and the new Cybertruck. At its core, the Gigapress is a die-casting machine, a process that is neither new nor unique. Casting has long been a foundational technology in automotive manufacturing, used throughout the industry's history. It's typically employed to shape critical components like engine blocks and transmission housings. However, it has never before been applied to such a large structural portion of a vehicle's frame. We could say the Gigapress is Tesla's superpower, the reason it has become a top-tier brand. These Gigapress machines are absolutely massive, colossal in scale. In fact, they're so huge they could easily swallow your entire apartment and still have room to spare. Crazy, right? They're so enormous that transporting just one of them requires more than 20 flatbed trucks. The company behind the gigapress is Idra, an Italian manufacturing group. Idra and Tesla appear to have been collaborating for quite some time, as Tesla has placed multiple orders with the company, some of which are still pending. This time, the installation of a colossal 50,000-ton gigapress at its Giga Texas facility. It's the mechanical core of Tesla's bold new plan to produce a Model 2 every 5 seconds and eventually scale to 15 units per cycle. But setting up a machine the size of a tilted 4-story building is no overnight task. The larger the machine, the more complex the installation. For reference, Xpeng's 16,000-ton press took roughly 4 months to become fully operational. A behemoth like Tesla's 50,000-ton version could take up to twice that time. But once it's running, it will drive a production line capable of sending shockwaves through the entire EV industry. Elon Musk has long emphasized that Tesla's biggest competitive advantage lies in production speed and efficiency. That's how Giga Shanghai can roll out a Model Y every 33 seconds. But as Tesla looked for ways to cut costs, streamline supply chains, and speed up time to market, Musk pinpointed a key bottleneck: the car's frame.
That, because it's probably have a few bugs, but it's going to be very cool. You'll want to invite your friends over and say, check this out.
Recognizing that components like engine blocks and cylinder heads will fade into irrelevance in a battery-electric future, Idra saw the need to evolve. That led to the development of the 6,000-ton and 9,000-ton presses, culminating now in the groundbreaking 50,000-ton version. At first glance, the gigapress might just seem like a tool for faster chassis production. And while that's true, it's only part of the story. Tesla's giant die-casting approach has replaced what used to be over 70 separate parts with a single unified casting. This not only cuts 10% off the vehicle's weight, Model Y being a prime example, but also reduces cycle times to just 90 seconds per unit. Beyond speed and weight reduction, the benefits compound. Tesla has reported a 40% cut in manufacturing costs and a 30% reduction in factory floor space. While it may sound counterintuitive, placing such a massive machine in the plant actually saves space. The reality is that it eliminates entire zones of robots, welding equipment, and multi-step assembly processes. Now, one machine does it all, applying a precise 50,000 tons of pressure in a single, flawless shot. How the 50,000-ton gigapress fits into Model 2 production. At the heart of this effort is the long-anticipated Model 2, a compact, affordable electric vehicle designed to hit mass-market scale at a speed and cost the auto industry has never seen before. Elon Musk has long maintained that production speed, not just product quality, is Tesla's ultimate edge. And he has numbers to back it up. The company currently produces a Model Y every half minute at its Shanghai plant. But to truly democratize EVs and hit the ambitious price point of $25,000 or less for the Model 2, Musk needed more than optimization. He needed to eliminate complexity at its root. The main culprit? The car's structural frame. Traditional car manufacturing relies on welding together hundreds of metal pieces with thousands of spot welds, bolts, and rivets. It's labor-intensive, costly, and leaves room for alignment issues and structural inefficiencies. Tesla's solution is radical. Cast the entire underbody of the car in a single shot using high-pressure molten aluminum. It's a method never attempted at this scale, until now. But calling it just a faster way to build chassis would be missing the point. Tesla's use of mega casting has already resulted in dramatic design improvements. On the Tesla Model 2, over 80 individual parts were replaced with a single rear underbody cast. Not only does this reduce assembly complexity, but it also shaves off 15% of the vehicle's total weight, translating into greater range and better efficiency. The actual casting process takes under 100 seconds, turning molten alloy into a finished component faster than you can get through a coffee break. From a cost perspective, the impact is equally massive. Tesla claims that the use of gigapresses slashes production costs by around 40% and reduces factory floor space requirements by roughly 1/3. While it may seem ironic that installing a giant machine helps save space, the math adds up. The press replaces entire zones of welding robots, conveyor systems, and manual workstations. What used to require 300 robots can now be handled by a single machine with surgical precision. In Tesla's vision, the Model 2 isn't just another electric car. It's the product of a system so optimized that each unit rolls off the line every few seconds. If Tesla can run its new press in synchronized cycles, it could hit volumes of 500,000 units annually per line, transforming the economics of electric cars. With Giga Texas now preparing for trial production runs and other facilities in Berlin and Shanghai rumored to receive similar upgrades, Tesla's global footprint is aligning with its global ambition. Musk has hinted that early prototypes of the Model 2 are already being tested internally, with a potential reveal by late 2025 and volume production targeted for 2026.
The Tesla team are making great progress in 1 year building a couple of machines, from scratch. That's remarkable. They're shining a spotlight on the importance of this technology, which we've been arguing for 30 years.
It's starting to look like the all-new Tesla Model 2 could break cover at virtually any point this year, and the headline everyone's buzzing about is a target price landing under 20 grand. Call it roughly $17,000. Sounds almost unreal, right? The company says its next wave affordable lineup is moving into scaled production in the first half of this year, using a new high-pressure gigacasting architecture that merges major body sections, cuts hundreds of parts, and shortens final assembly time. Lower battery material intensity and a simplified interior package help too. Elon Musk has also claimed the Model 2 is poised to become the highest volume vehicle program in the company's history, with lifetime output modeled in the tens of millions, north of 40 million units in some internal scenarios floated alongside Master Plan Part 3. Design? Word is Tesla's keeping the final sheet metal revealed tightly under wraps, so expect something that catches a lot of people off guard. What matters operationally is speed. Musk says this car will move through production dramatically faster than Model Y, multiples faster, in fact. We've been talking about the cheap Tesla forever. Plans shifted, paused, resurfaced, wash, rinse, repeat. Now, backed by Musk's latest comments and Tesla's own manufacturing moves, it finally appears real. Early build work is underway, and a formal announcement could drop any day because the car is edging toward retail, and Tesla could use the volume boost right now. Pilot tooling reportedly started at Giga Texas, with parallel localization work in Mexico and Shanghai to hit regional cost targets and qualify incentives. As mentioned above, the Model 2 is slated to follow on the current Model Y and Model 3 production lines, but instead of the 6,000-ton Giga press used for Model Y today, it will be manufactured with a new generation Giga press. Although its basic operating principles are similar to the 6,000-ton and 9,000-ton die-casting presses you've seen tied to Model Y, the new 50,000-ton Giga press scales everything: clamp force, shot size, tooling envelope, thermal management, to enable far larger structural castings for Tesla's next-gen low-cost platform. Think of it as the same fundamental machine class, just massively upsized and optimized for multi-section unibody-style structural pieces that can collapse dozens or hundreds of stamped and welded parts into a couple of mega castings. The process still starts with metal. Tesla feeds virgin aluminum ingots plus clean, sorted casting scrap reclaimed from prior shots into a gas-fired melt furnace running at roughly 850 degrees Celsius. Once liquefied, surface dross is skimmed off. The melt is then transferred through an insulated launder to a sealed electric holding furnace stabilized in the approximately between 750 and 850 degrees Celsius window. Using two furnaces, one to melt, one to hold, lets Tesla keep chemistry tight and temperature steady while staging rapid repeat shots for high-tact production. To control oxidation and maintain alloy integrity, the furnace headspace is blanketed with nitrogen. Operators also inject argon during degassing, spin a rotary degasser to drive out dissolved hydrogen, and push the melt through multi-stage filters. Silicon carbide ceramic media are common. that capture inclusions larger than 25 microns before metal ever sees a die cavity. That's the material conditioning stage that underpins structural casting quality. Before each cycle, the die halves are mist lubricated. A programmed robot sprays on the order of 30 to 40 milliliters of a soy oil-based release and conditioning fluid across the tool surfaces, basically the industrial equivalent of greasing a baking pan so the part releases cleanly. The press then pulls a deep vacuum on the die cavity to purge trapped air pockets that could create porosity when metal hits. The shot sleeve and plunger, piston, also receive a light lubricant charge, typically between 5 and 10 milliliters per shot, to cut friction, improve fill consistency, and extend component life under extreme thermal cycling. With the cavity evacuated, molten aluminum is metered from the holding furnace into the shot sleeve. A high-speed hydraulic or servo-hydraulic piston then rams the metal into the closed die at very high linear velocity. For comparison, the 6,000-ton cold chamber presses used on Model Y push a bit over 100 kilograms of metal at roughly 10 meters per second, cycling in about 18 to 20 seconds and yielding on the order of 180 good castings per hour, roughly 4,000 parts across 3 8-hour shifts when running flat out. Those numbers are ballpark, but they give you a scale reference. The clamp tonnage rating isn't about shooting metal. It's about holding the die shut against internal metal pressure during fill and solidification. The 50,000-ton class machine doesn't ram aluminum with 50,000 tons. It uses that massive clamp force so the die halves don't flash apart when a much larger metal volume slams in at speed. The bigger envelope lets Tesla combine what used to be multiple subcastings, or stamped and welded assemblies, into single monolithic structures. For the Model 2 small vehicle platform, Tesla is targeting full front underbody structure, roughly from the driver's footwell forward, as one casting and the rear underbody, from the rear passenger footwell aft, as another. The longer-term stretch goal Musk has teased, multiple vehicle frames in a single shot, would exploit the tonnage and platen area to gang several cavities in one machine, though we'll need to see how tooling logistics and thermal balance shake out before calling that production ready. After fill, the casting remains clamped while metal solidifies under pressure. Once the solid fraction crosses the release threshold, ejector pins push the part free at roughly 400 degrees Celsius. The still-hot structural casting is immediately transferred to a quench bath, or intensive forced air spray quench cell depending on line setup, to pull temperature down quickly, typically from 400 degrees Celsius to 50 degrees Celsius. Rapid controlled cooling reduces certain shrink porosities, tightens dimensional stability, and sets up the alloy for subsequent heat treat or paint bake tempers. Meanwhile, the die closes back up the thermal gap. Tooling faces are cooled and rebalanced to a working range near 185 degrees Celsius before the robot sweeps, relubes, and stages the next shot. Depending on shot size and alloy, the 50,000-ton cycle time target is expected to be materially longer than the 6,000-ton baseline on a per-shot basis. But because each shot yields much more structure, potentially multiple subframes, net vehicle throughput per hour rises sharply. But now they're unlikely to reach U.S. showrooms until the current U.S.-China trade friction cools. But Tesla's upcoming budget models are moving ahead elsewhere. Recently, Vice President of Vehicle Engineering Lars Moravy pulled back the curtain on how Tesla is approaching its lower-cost lineup. In his words, with the refreshed Model 3 and Model Y, we've proven we can deliver compelling cars at sharp pricing and add meaningful features. The mission isn't to ship something worse than what we already build. Models due over the next several months will carry familiar Tesla proportions and design language, he said, and, critically, will be priced so ordinary buyers can actually take one home. One major design constraint: cost discipline, tied to existing production assets. To land below the psychological $30,000 threshold pre-incentive in many markets, the car must ride current Model 3 and Y lines instead of a bespoke factory, which also hints it could diverge from the more radical Tesla model. Two concepts. Word out of China is that pilot-build mules, essentially short wheelbase Y derivatives, have already started running. A local news outlet reported limited scope trial production last month. Meanwhile, Toyota has rolled out its new flagship electric sedan, the BZ7, in a bid to claw back ground in China, where domestic EV champions have been eroding its share. Co-developed with manufacturing partner GAC, the BZ7 squares off against high-volume mid- and upper EV sedans, including Tesla's Model 3, BYD's Seal, and XPeng's P7 Plus. If U.S. EV subsidies fade, does a $25,000 or $17,000 Tesla Model 2 still win your wallet? Or do you jump to BYD, Toyota's BZ7, or stick with gas? Why? Please share your opinion in the comment section below this video. Thanks for watching our video. If you want to explore more exciting information about Tesla EV or Tesla Bot, don't forget to hit the like button and share this video. Also, make sure to subscribe to Tesla Car World and turn on notifications so you never miss our latest videos. We appreciate your support and look forward to seeing you in the next video. Goodbye.